On the morning of November 25, a faint echo appeared inside NASA's Deep Space Tracking Network. It did not look like a comet. It did not behave like an asteroid. And at first, it seemed like nothing more than residual noise left behind by the chaos surrounding 3I Atlas. But as technicians filtered the data, that weak reflection refused to disappear. Instead, it returned at predictable intervals, matching no known catalogued body. NASA expected the region to be empty. It had already been surveyed after 3 Atlas passed through. Yet now a second object was slowly revealing itself, moving along a trajectory that mirrored Atlas's path just enough to raise questions. Not close enough to suggest a direct connection, but not far enough for coincidence to fully explain. The detection marked the beginning of a new investigation, one grounded not in fear or speculation, but in quiet scientific curiosity. Interstellar visitors are already rare. 2 arriving in the same observational window challenges almost every statistical model used to estimate how often star system debris enters ours. Today we explore what NASA has discovered so far, what remains uncertain, and why this second object is quickly becoming one of the most mysterious silent travellers to enter the solar system in years. The signal first appeared as a narrow spike in background noise. Goldstone's radio dishes were performing a standard calibration sweep, clearing out solar interference that had intensified after recent flares. During this routine pass, analysts noticed a consistent reflection that did not fit the typical profile of dust, plasma, or equipment feedback. It was subtle, almost ghost-like, and if it had surfaced only once, it would have been dismissed without hesitation. But an hour later, Canberra Station detected the same signature at a slightly different angle, confirming that the pattern was real and not a localized artifact. At first, researchers assumed it was a forgotten asteroid drifting through an outer corridor. NASA maintains detailed catalogues, yet objects occasionally slip through, especially if they are small, dark, and non-reflective. But when analysts attempted to match the signal to the orbital paths of known bodies, nothing aligned. The timings were off, the angles were off. Even the Doppler shift curve implied a velocity too high for a typical solar system object. What made the situation even stranger was the spatial context. The signal was emerging from the same region 3I Atlas had passed through. That area had already been swept clean in earlier scans. It was not a place where another visitor should appear so soon. Interstellar objects travel alone, separated by enormous distances and chaotic trajectories. The odds of 2 unrelated objects entering the solar system on similar timelines are so small that most models never seriously consider it. As the data accumulated, the team realized this was no statistical fluke. The object was real, it was moving, and its path curved in a way that mirrored the wake Atlas left behind. Not tightly, not deliberately, but unmistakably enough that the detection forced NASA to reopen files they thought were closed. After 3 days of continuous tracking, the object's path became sharper. Software reconstructed a hyperbolic trajectory, which is the unmistakable signature of an interstellar origin. This was the first red flag. Hyperbolic paths are extremely rare events. Atlas had already challenged probability once. A second hyperbolic object arriving within the same observation window suggests something more complex happening far beyond our solar system. The inclination of the trajectory deepened the mystery. It sat only 3 degrees off Atlas's incoming line. 3 degrees is not enough to suggest a shared orbit, but it is close enough to trigger theoretical questions. Could both bodies have originated from the same disrupted star system? A collapsed protoplanet? A shattered dwarf planet? A debris cloud flung outward by a passing star or supernova? None of these ideas are impossible, but they require conditions that occur only once every millions of years. And even if such an event created multiple fragments, the likelihood of 2 of them entering our solar system within months is almost too small to compute. Another complication emerged when the velocity was calculated. The object was slower than Atlas, yet still too fast to be gravitationally bound to the Sun. This implies the object has been drifting for enormous timescales, perhaps hundreds of millions of years, long enough for radiation, dust collisions, and interstellar drag to erode and reshape its structure. But the biggest surprise came when the reconstructed trajectory showed a subtle curvature, exactly through the region where Atlas caused magnetic and plasma disturbances. It did not appear intentional, but it also did not appear entirely random. The trajectory raised one unavoidable question. Did both objects experience the same interstellar event before drifting toward us? NASA's ability to measure small dark objects is limited until they move closer to the Sun. This second visitor is unusually faint, reflecting sunlight in a weak but rhythmic pattern. That rhythm became the first clue about its structure. A slow oscillation in brightness typically suggests rotation, but this object rotates in a way that feels too stable, too smooth. Natural asteroids often display jagged peaks in brightness, as irregular surfaces scatter light unevenly. Here the pattern is almost gentle. Initial estimates place the diameter between 1 and 3 kilometers. But density remains unknown. If the object is metallic, that size could mean a mass far greater than any comet of similar scale. If it is carbon-rich, it may be porous and lightweight. Astronomers attempted to model surface texture using brightness curves. The results were inconsistent. Some readings hinted at a highly reflective surface. Others suggested organic compounds or a crust of dark, weathered carbon. The lack of outgassing further complicates analysis. A quiet interstellar visitor is harder to decipher than an active one. Most puzzling is the object's shape stability. Even small irregular bodies tumble as they rotate. Yet this object maintains a steady orientation, suggesting either a highly symmetrical structure or a rotational axis perfectly aligned with its incoming path. Both scenarios are possible, but neither is common. This stability may explain why the object remained hidden for so long. It reflects light predictably, making it harder for earlier surveys to separate from background noise. NASA now believes the object may be denser than typical comets, colder than typical asteroids, and potentially coated in material that absorbed cosmic radiation during its long journey. Whatever its true shape, it does not behave like debris casually wandering in from interstellar space. Infrared spectroscopy from the IRTF telescope revealed an unexpected signature. The object contains complex carbon chains that absorb light differently than those found in 3I Atlas. This finding immediately challenged the early hypothesis that both objects might share a common origin. 3I Atlas exhibited a mixture of volatile compounds, including carbon dioxide, cyanides, and traces of organics rarely seen in solar system comets. But this second object shows none of those extremes. Instead, its spectrum resembles something older, something processed by cosmic radiation for a far longer period. These carbon chains suggest exposure to high-energy particles over vast stretches of time, possibly hundreds of millions of years. Scientists propose several natural explanations. One is that the object may have formed in a colder region of its parent system, preserving carbon-based materials without significant heating. Another possibility is that it once belonged to an ancient debris cloud that has long since dispersed. The difference in carbon signature does not rule out a shared origin, but it makes the connection far less likely. Yet it deepens the mystery in another way. Why would two interstellar objects with dramatically different chemical fingerprints arrive along such similar trajectories? One speculative but scientifically grounded idea is gravitational shepherding. If both objects travelled through the same interstellar environment, they may have been influenced by a massive gravitational source, a rogue planet, a neutron star, or even remnants of a multi-star system. If such a structure sent debris outward over billions of years, multiple fragments could scatter across interstellar space. Only a fraction would ever enter another star system, and only a tiny number would cross paths with ours. This carbon discrepancy makes the object unique, ancient, and potentially one of the most chemically interesting visitors we have ever detected. Comets evolve dramatically as they approach the Sun, vaporizes, dust erupts, tails form under solar wind pressure. These processes help scientists determine composition and structure. But this object remains silent. Its temperature has increased steadily since detection, yet there is no halo, no jets, no visible activity. It is behaving more like a carbon-rich asteroid than a comet, but its speed and trajectory eliminate the possibility that it belongs to our solar system. NASA's models show that even dormant comets release measurable gases as internal ice pockets fracture under heat. The absence of such activity suggests one of three possibilities. First, the object may be composed of extremely non-volatile material. Some interstellar bodies are formed in ultra-cold environments where volatile compounds are rare. These bodies remain stable even near stars. Second, the surface may be coated in carbon so thick that it insulates underlying ice from vaporizing. Long exposure to interstellar radiation can create a hardened crust capable of trapping volatiles for extended periods. Third, the object may simply be devoid of volatiles, making it more similar to a rocky fragment than a comet. This lack of outgassing also explains its predictable rotation. Without jets pushing against its surface, its orientation remains unchanged. For NASA, this stability is valuable. It allows precise trajectory modelling and better forecasting of its future path. The most intriguing aspect is that quiet interstellar visitors are rarer than active ones. Most interstellar travellers lose material as they heat up, leaving detectable chemical trails. This one remains sealed and cold even as it draws closer to the sun. The silence of this object raises scientific curiosity, not because it suggests artificiality, but because it represents a category of interstellar material we rarely get the chance to observe.